a platform for atomic fabrication and in-situ synthesis in a scanning transmission electron microscope. This manuscript was published in the journal Small Methods in 2023. The engineering of materials that will enable the harnessing of quantum properties of matter for information science requires the enhancement of our technological ability, especially in the areas of material growth, manipulation, and defect engineering. Atomic scale precision in the structure of matter will be a key driver for eliciting quantum properties and manufacturing devices capable of harnessing these properties. Successful use of a scanning transmission electron microscope for atomic manipulation has demonstrated a possible approach toward such capabilities. Recent work has highlighted the ability to put many different types of atoms in graphene, and has shown that top-down atomic patterning is possible. Those studies relied upon source materials that were introduced as nanoparticles on the graphene surface. That approach is not easily amenable to a device fabrication workflow. In a recent article published in Advanced Materials, we put forward the idea that in-situ synthesis processes would complement and enhance atomic manipulation efforts. The material transformations observed in the STEM can be thought of as reactions within an atomic-sized reaction chamber defined by the beam sample interaction volume. If one conceives of this as a reaction chamber, or a chamberless synthesis environment, it becomes natural to think about material transformations from a synthesis perspective. That is, one begins to think about controlling environmental parameters to drive a desired change. This is a marriage of bottom-up synthesis processes and top-down influence. One of the critical control parameters available for synthesis is the supply of a precursor material to the substrate of interest. This capability is generally not available in a STEM. Nevertheless, in that work we presented a simple way this could be accomplished using existing hardware that does not require modification of the microscope. In this work we present the initial testing of an in-situ evaporative delivery platform aimed at supplying atomized material to a substrate to enable the combination of synthesis and atomic fabrication techniques. The design is composed of two main parts, a printed circuit board and a metal base plate, that sandwich the sample between them and allow electrical contact to the sample. The sample dimensions are based on the protochip's heater chip and will allow electrothermal experiments with the chip itself. This assembly slides into a neon electrical cartridge and is then fully compatible with the standard microscope operation. The main feature of this platform is the additional incorporation of a heater filament located at the end of the PCB, which can be independently heated to evaporate materials in situ. A picture of the assembled device is shown here, with a magnified view of the filament. Here's an image of the platform sitting in the pole piece of the microscope, and with the lights off, we can activate the filament and see it glow. As an initial proof of concept, we applied a small amount of solder to the filament and evaporated it in situ. The substrate used in this experiment was a silicon nitride membrane. Here are the before and after images of the sample. We can clearly see that we have formed many nanoparticles across the silicon nitride surface. In addition, if we monitor the vacuum reading at the pole piece, we can clearly observe the pressure spikes when the filament is activated, which gives us a rough idea of how rapidly the material is being evaporated. We are primarily interested in the ability to deliver single atoms, so while getting nanoparticles is a great initial step, showing that we can thermally deliver material, we would like to deliver a smaller amount and from a pure source, not solder. To this end, we coated another filament with 500 nanometers of tin and switched to a twisted bilayer graphene substrate. We first heated the graphene to clean it and then held it at 500 degrees Celsius. As well, we damaged a few locations with the electron beam, shown here. Then we activated the filament to thermally deliver the tin. Here is a comparison between the before and after images of the graphene sample. We can see that the tin, which shows up bright in this imaging mode, has attached mostly to the folds and step edges of the graphene. But several bright spots have also shown up at the damaged locations. Zooming in on these bright locations, we can see that we have grown what appear to be 2D tin flakes. In addition, we found many single tin atoms across the sample, mostly anchored at step edges and other defect locations. This suggests that we were indeed able to deliver atomized tin to the sample, and represents the first step toward combining synthesis and atomic fabrication in the STEM. The development of a new platform for atomic fabrication and in-situ synthesis in a STEM represents a significant change in thinking about what is possible. This approach of combining bottom-up synthesis processes and top-down influence has the potential to break new ground in atomically precise manufacturing. The successful testing of an in-situ evaporative delivery platform demonstrates that it is possible to deliver single atoms and initiate growth processes in a STEM, and represents a crucial step toward realizing this potential. Links to the publication may be found in the comments section below.